Okay, so now we're going to talk about something called formal charges and resonance. All right. So it's important to note that sometimes when you're doing Lewis structures, it's more than one possibility. And when that's the case, we're going to evaluate the different possibilities based upon a formality called formal charge. We're going to do some calculations and pretty much figure out with some easy math which one of the two possible structures are, better. Okay. Now, a formal charge of an atom in a molecule is the hypothetical charge that an atom would have if the electrons in fact were were shared equally. So just like with oxidation numbers, formal charges are not charges, okay? This is sort of a way of keeping track of things. It's just like an accounting game. All right? So they matter, but they're hypothetical. Okay, so here's how formal charges are defined. Formal charges are defined like this. You have the valence electrons, which just comes from the group number, okay, minus all of the lone pairs, minus half of the bonding electrons, okay? This will make total sense. Have you done a bunch of these? It's going to make total sense. Now, the sum of the formal charges has to equal the charge of the whole species, okay? It's 0 for a molecule, of course, because molecules are neutral, right? And for polyatomic ions, it's the charge of the ion. All right? And we use this rule to check we use formal charges to check our Lewis structure. All right, so the quality of a Lewis structure can be determined by the distribution of formal charges. The best Lewis structures will have the lowest formal charges. All right? Adjacent formal charges, they'll also have adjacent formal charges of 0 or of opposite sign. You wouldn't want to have two formal charges which are positive next to each other, two negative next to each other. And if there must be an atom with a negative formal charge, it ought to be with the most electronegative atom. Okay, so this is going to make a lot more sense after we practice a little bit. All right, so there's some exceptions to the octet rule. And on rare occasions, the correct Lewis structure does not obey the octet rule. Right? We've already seen some exceptions. And formal charges can be used to help us to predict these instances. All right. Now, let's talk about resonance forms. In certain cases, a single Lewis structure does not adequately predict the properties of a molecule. I'll give you an example in just a minute. For these compounds, two or more Lewis structures can be drawn. Equivalent Lewis structures can be drawn. And these individual Lewis structures are called resonance structures. We'll see why in a minute. Individual resonance forms do not exist. They do not exist. Resonance is when the actual structure is a mix of the two. Okay, so resonance, if two or more Lewis structures with the same arrangements of atoms can be drawn for a molecule or ion, then the actual distribution of electrons is the average of that shown by the various structures. All right, so we're going to take a couple slides now to tease that out a little bit. Let's consider nitrate. So with nitrate, if I were to ask you to draw the Lewis structure of nitrate, you might draw this here, right? This is nitrate. So you have a negative total, and then you have a single bond, double bond, and so on, right? Now all three NO bonds are identical. By the way, let's do formal charge for a couple of these. Let me do formal charge for this. So let's do formal charge for this one right here. The formal charge is equal to the valence number, and this is valence number. This is in group 6, so it's going to be 6 minus all of the lone pairs. There are 6 electrons that are unpaired. You see them right there? I mean unshared, right? And then half of the shared, and there's 2 electrons here that are shared. Okay, so this is 6 minus 1, which is equal to minus 1. Right, so the formal charge in that oxygen is minus 1. Okay, this is the same. It's going to be minus 1. And this nitrogen then, watch this. The formal charge on the nitrogen, do a different color here. The formal charge on the nitrogen is equal to, that's in group 5, right? It's in group 5. It has 5 valence electrons. And it's got 0 unshared. And it looks like it's got 8 shared, right? 8 is equal to 5 minus 4 is equal to plus 1, right? So it looks like that's got a plus 1 formal charge. And look at this. What a coincidence. Minus 1 plus 1 gives you minus 1, right? Okay, so this is a legitimate Lewis structure for nitrate, but so is this. This is the same thing, right? And so is this. These are all three different legitimate structures for nitrate. Well, it turns out then, since they're legitimate and equivalent, they are resonance structures one of another. What that means is that these electrons here are equally shared between all of them. Now, importantly, all three NO bonds are identical in their properties. If we were to measure this with spectroscopy, we would find we don't have two different kinds of bonds. We don't have single NO bonds and double NO bonds. We do not. We actually have all three of them are identical. And funny enough, the bond length is in between the length of a single bond and a double bond. In other words, this bond here is really in between a single bond and a double bond. It looks like it's single, right? But that's just a formality. It's just how we draw it. All right? So finally, here's some notes on resonance. A resonance hybrid never possesses a structure described by either resonance form. A resonance hybrid does not fluctuate between the different resonance forms. Electrons are not shifting between the different structures. They actually are a mixture of the structures, okay? Resonance arises when two Lewis structures or more are equally plausible. And then finally, resonance forms only differ in the distribution of electrons, not in the arrangement of atoms. All right? In other words, the atoms are all connected exactly the same. It's only the electrons that are moving around. So here's some resonance structures, and you see the atoms themselves don't move. Okay, so that's a fast introduction to formal charge and to resonance. Let's go practice.